Hi, I'm Mr. V. This is Illustrative Mathematics. We're in Unit 6, Coordinate Geometry. This is our first lesson from this unit. There are about 18 sections in this unit, and this is the last one that we will cover this year. We'll start with rigid transformations in the plane. The objective of this lesson is that by the end of the lesson, you should say, I can prove triangles are congruent using coordinates. And I can reflect, rotate, and translate figures in the coordinate plane. We start with asking this question: how far is point A from point B? And after you try that, you can ask for the hint and it'll tell you. I'm going to show you that this is perhaps the most important coordinate geometry problem that we will discuss all year. And the reason is because it keeps coming up. How do you find the distance between 2 points? There is a distance formula, but we're going to use something that's even more commonly known to us. We are not going to use taxi cab geometry, and there is such a thing, if you can believe it. This is 3 and this is 4, the way the taxi cab would drive. We want to know how the bird flies. How far is this distance? And you'll notice I've drawn a Pythagorean triangle here. I've drawn a right triangle, and we can use the Pythagorean theorem. We can say a squared plus b squared is equal to c squared. If you don't recognize this as a 3, 4, 5 Pythagorean triple, we can substitute the values and find it. We know that 3 squared is 9 and 4 squared is 16. Together, this makes 25, and this is c squared. So to do the inverse operation to find what c is equal to, we'll take the square root of, that's the inverse of squaring, and square root of both sides of the equation, and you get 5. And like I told you, this is a 3, 4, 5. And that would be one way to discover how far it is. Another question, though, that comes up is, how could you map from A to B? What transformation would get you from A to B? And one way of doing this would be to translate. So we could say, I'm going from A to B. How can I do it? One way is to use a vector AB. And this vector would have components that would be in the x direction. It's going to be 4 to the right, and it's going to be 3 down. So you could say 4 right and 3 down. Or you could write it in a vector notation. Sometimes you see this using these type of brackets, and it's typed, but since I'm typing and I don't have access to those readily, I can use brackets, which is a common way of doing it in some circles. We're going to go 4 to the right in the x direction and a negative 3 in the y direction. So this would be another way of writing it. Or I could say, I'm going to add this to my A. Now, I'm not going to go the other direction. I'm not going negative 4, 3, because that would put me from B to A. So I want to make sure I'm going in the right direction. I could also say that I'm going from x and y. I'm going to translate this to, in the x direction, we're going to add 4. And in the y direction, we're going to subtract 3. And this is a notation that we will be talking about later on in this trimester. But the idea here is that you could translate the one point A to get to point B. A second rigid transformation, besides translation, is rotation. And then when you rotate, we're going to rotate, you have to have a point that you're going to rotate around, the degrees, and the direction. So if I go by the midpoint of AB, I'm going to go 180 degrees. If I go 180, I don't have to specify counterclockwise or clockwise because it would be the same. It would put me in the same one. So either way, but I'm going to go around the midpoint. A third type of rigid transformation that we could do to get to this is to reflect. And maybe you will recall reflection. When we reflect, we're going to go across the perpendicular bisector of segment AB. That means that it has to be perpendicular to segment AB. If AB has a slope of, what is this, 2 and then 1, I don't know if this is 2. Maybe it's going to be steeper than this. I don't know. Let's see if I can do this a little better. Try to do this a little better. Here we go. So I think I have to go up this far. No, that's too far. I'm going to go across the perpendicular bisector of this segment. So it has to be perpendicular and it has to be the midpoint of the segment. So that's the way that we would reflect across it to get it. Going back to my Desmos, we have a card sort. And in the card sort, which I could do here for you really quickly, is to show you that I have three groups. I have reflections, I have translations, and I have rotations. And as you do these, you can check them on the next page to see how many that you got correct. You will notice that this one looks like it's a rotation, and I can check it on the next page. Yeah, it's getting better. I've got one pair that's correct. This one, I notice my D goes to this D. This would be a translation. And this one, you would think it's a translation, but the S is here and this S is here. This would be a rotation. Here I've got a rotation. This is a reflection. I'm going to make it to where the cards match up. The N is at this end. The N is this one. This would be a rotation. Here I've got a reflection, a translation, and a translation. When you get them all correct, it'll say yes here. You'll also get all the green ones here saying it's a go. Now let's translate with coordinates. Here is an activity. This explains how to do it. You can follow the GeoGebra and try it. When you are done, you'll end up with this figure. And the real question I have is, how do you know that these three figures are, these three triangles, or these three figures are congruent? How do you know that? And one way is because you created it by mapping the one onto the other using a finite set of rigid transformations. For example, we translated this figure H from here to here, which got me to this point. And then we rotated it 90 degrees around this point. Not 90 degrees, excuse me, back up, 90 degrees around this point, which would map me on there. A second way of getting from here to here, we reflected across the y-axis, which was this figure, and then rotated it 90 degrees around the origin, this way, counterclockwise. So one way to know it is that they are all, that you could map it with the rigid motion transformations. You could also have looked at the lengths of each of these. You could say, well, this is 2, 2, and 3, and this length. Now this length, this is 1 by 2. So if we use the a squared plus b squared is equal to c squared, we could do 1 squared plus 2 squared is equal to c squared. This is 1 plus 4 is equal to c squared, or 5 is equal to c squared. This distance is the square root of 5 here and here and here, and each of these have all the sides that are congruent. So that's another way of knowing that the figures are congruent. Well, in the next activity, we check this. We're going to calculate the side lengths, calculate the angles, and we're going to specify rigid transformations that will map the one onto the other. Well, I know that AB is 3, and I know that CB is 2, and you can see I got it correct. Now this one would be 2 squared plus 3 squared. That's 4 plus 9, which is 13. So SQRT, square root of 13, gets me correct. And all of the sides here are going to match up. This is going to be 3, 2, and square root of 13. Now let's look at the angles. What are these angles? I'm going to tell you that B is 90. And I could tell you that E is 90. And now all I have to do is find the others. We're supposed to round these to the nearest unit. That's what it says in the instructions. So if we go to our triangles here, from angle A, this would be the opposite side, and it's 2. And this side is 3, and this would be the adjacent leg. So which of our trigonometric ratios will do that? Is it SOHCAHTOA? It's the tangent. The tangent of the angle of A degrees is equal to the ratio, 2 over 3, opposite over adjacent. So to find this, do you remember your trigonometry where we take the inverse of the ratio is equal to the angle? So our angle is equal to, down here, the inverse of the ratio is 34 degrees, rounded to the nearest degrees. And if this is 34, this is 90. What do you have to add to 34 to get to 90? Or subtract 34 from 90 and you get 56. So when we put those numbers into our business here, this would be 34 and 56. Angle D is 34, and this is 56. So we can find all of the angles and all of the sides. And we know that they're congruent because all of the angles and all of the sides are congruent. We have a saying for that in math. We call that CTC. The corresponding parts of congruent triangles are congruent. But wait, was it necessary to show that all three sides that you could measure and all three angles that you could measure were congruent in order to prove that they are congruent? Do you remember any of the shortcuts that we had from the first trimester of this course? Maybe you do. Maybe you don't. There were some that were valid, and there were some that were invalid. Invalid. The valid ones were the side, triangle congruence theorem. If you know three sides of one triangle are congruent to three sides of another, then the two triangles are congruent. What about the side, where the angle is the included angle? Or how about the side, angle, which also implies the angle, side? These are all valid shortcuts. There's one that is not valid, or it is valid sometimes. And this would be the donkey theorem, the ASS or SSA theorem. You recall, if I have an isosceles triangle, the base angles are congruent. These two sides are congruent. Here we have angle, side, and I put in a third side. Are these two triangles congruent? No. It's valid if the angle is 90 degrees or more, or if the angle that is opposite, the side that is opposite the angle, is the longer of the two sides that are given. So this S is the longer of the two sides. Another invalid shortcut is the angle, or angle. This is auto insurance. This is also the dilation. So if you're going to dilate two triangles. So you didn't have to prove it all. You didn't have to prove all that together anyway to prove that the two triangles are congruent. Now, we could also do a transformation, and I will do that here if I can. I'll try to make this smaller. Let's see if I can do this. So I'm going to translate by defining a transformation. I'm going to show you how to do this, so if you wanted to, you could. We're going to translate, choose where we're going from, point A to point D. This is the object I want to translate. I'll apply it. I'm also going to change the color of it so you can see that this is what I'm dealing with. And now I'm going to rotate this around point D. So I have to define the transformation, define a rotation. It's going to go around point D. What is it that I'm going to rotate? I'll start with these two parts. I'll also rotate this. Oh, I need to apply this. And I'm going to apply this piece as well. And you can see that it all makes out. So if I were to describe this in words, I would say, number one, translate. ABC, triangle ABC. I'm going to use the vector. I'm going to use the vector notation. I'm going to say I'm going to go a -5 in the x direction and a -1 in the y direction. And then number two is I'm going to rotate the A prime, B prime, C prime about D 90 degrees counterclockwise. And that's it. That describes the rotation, that describes the transformation that will map ABC onto DEF. We know that they're congruent because of the CPCTC and because of the side triangle congruence theorem. So we can map the one onto the other using a finite set of rigid transformations. Translate, rotate, done. Okay. Let's see what else have we got in this lesson. A single transformation would do it, and you can try this on your own. I could show you, but if you're interested, I'll show you after class sometime. Let's see. Why can you use trigonometric ratios to find angle measures? Well, that's the big idea. In the coordinate geometry, we have the lengths, and so we can use this to find the ratios, the angle measures. In the activity synthesis, you can read this on your own. It says that we don't need all 6 parts. We can show this with the side. And further, in the lesson synthesis, I could take this triangle, and I'll move it onto my whiteboard. I want to make a figure that is not just a simple translation, because any Yahoo can do that. I want it to have at least 2 transformations. I want it to be a composition, 2 transformations that would map the one onto the other. So if I start here at -4 and I go like 1, 2, 3, and I go this far over to here, I could look at these segments. This is 3, this is 3. And I could look at these other segments and say this is 3 and 6. This would be 3 and 6. So using the Pythagorean theorem, 3 squared is 9, 6 squared is 36. This would be the square root of 45, or 3 times the square root of 5. This is the square root of 45. I can also do this other side, and I'll do this in the pink color, I guess. And I know that I've got 6 and 6. This is half of a square. Do you remember your special right triangles? Half of a square. 6 times the square root of 2. All three corresponding sides are congruent. Therefore, the two triangles must be congruent. Another thing I could have done was I said, translate this triangle from D prime to D, and then reflect it across ND. So there are two ways of showing that they're congruent. One is with the sides, and one is by rigid transformations. That's kind of the big idea from this lesson. The proof, maybe I show it by and when you graph it, it would show up there as well. So you could use the side triangle congruence theorem, or you could use a special sequence that would map the pre-image onto the image. That's the big idea. There's a lesson summary, and it says these same things. You can read that on your own. And finally, we have these two triangles. If I were to take this, I'll just copy this over, and I'm going to describe for you a transformation that would map the one onto the other. One is if I use a vector, directed line segment, I'm going to go 3 in the negative x direction, 2 in the negative y direction. So I'm going to translate ABC, triangle ABC, by vector -3, -2. That's going to put it right here. The next step would be to reflect it. We'll reflect it across what? Across the middle, right there, this line right here. This line is defined as x is equal to -1. So reflect. So translate, and then reflect. That would map the one onto the other. Further, so translate. And then reflect across x is equal to -1. You could also look at the side lengths. The square root of 5, the square root of 5, and this is the square root of 10. The square root of 5, the square root of 5, the square root of 10. And that's pretty much it for today. So good luck and success.